Welcome to simple harmonic motion. So recall in an undamped free system, so in an undamped free spring mass system, the displacement is modeled by y double prime plus k over m y is equal to 0. Here, where k is the spring constant, and m is mass. And then note that we had k over m was actually the same as g over change in L, where g is the acceleration due to gravity. And delta L, lowercase l, is essentially the equilibrium stretch of the spring. So let's just consider an undamped free spring mass system in general. So we have y double prime plus k over m y is equal to 0. And then we could have initial conditions, y of t naught is y0. I'm going to use sloppy notation here. And y prime of t naught, I'm just going to label it as y0 prime. So again, that's a little sloppy notation, but that's just how I'm going to do it for the notation. So note, if we set w naught as the square root of k over m, then the equation becomes y double prime plus w naught squared times y is equal to 0. This then has characteristic equation. R squared plus w naught squared equals 0. Or omega naught, I think, is technically what it's supposed to be. And then let me update my screen. So I'm going to actually say that's omega naught, not w naught. Then we wind up getting here that R is plus or minus omega naught times I. So we get general solution. Y is equal to C1 times cosine of omega naught t plus C2 times sine of omega naught t. So what we are going to do is we are going to manipulate this slightly into another form. So now let's manipulate this into another form. actually, before you do that, if we actually had initial conditions, we could solve for C1 and C2. So we could use the initial conditions to solve for C1 and C2. With cosine and sine, it's pretty simple. If our t is 0, the sine term will always disappear in y or in y prime. And so you have a pretty simple equation to solve for C1 and C2. And then once you have found C1 and C2, we can manipulate this equation into an alternative form. So we can manipulate y equals C1 cosine omega naught t plus C2 sine omega naught t into an alternative form where it is easier to sort of see what's going on with the motion. So into an alternative form to better be able to study the motion. So essentially what we're going to do is we're going to treat C1 and C2 like X and Y and convert them into polar coordinates. So we'll treat C1 and C2 like X and Y and convert them into polar coordinates. So we'll take R, capital R, to be the square root of C1 squared plus C2 squared. And then we'll have C1 is R cosine of phi. And C2 is R sine of phi. Right, so then we can go ahead and rewrite this. So the equation we wind up with y is equal to R times cosine of phi times cosine of omega naught t, and then plus R sine of phi times sine of omega naught t. And now we are going to use an identity. So we are going to use the fact that cosine of alpha times cosine of beta plus sine of alpha times sine of beta is just cosine of alpha minus beta. We will take omega naught t to be our alpha and phi to be our beta. So with alpha being our omega naught t and beta being our phi. And so what we wind up getting is that y is just R cosine of omega naught t minus phi. So it's much easier to analyze a trig function if we just have one trig function. We can easily analyze this for frequency, amplitude, period, etc. So that's what we will be doing. I'm going to just give myself a little more room quickly. So essentially what we have is, so in summary, we can rewrite our solution. Y equals C1 cosine of omega naught t plus C2 sine of omega naught t as y equals r cosine of omega naught t minus phi, where r is the square root of C1 squared plus C2 squared, and phi satisfies C1 is equal to r cosine phi, and C2 equals r sine phi. You could rearrange both of those. So we have cosine phi equals and sine phi equals. And then we'll pick phi between negative pi and pi. And then once we have this, we can go about determining our period, our frequency, our amplitude, and our phase angle. So note, we can determine period, frequency, amplitude, and phase angle from this form. So our period would be 2 pi divided by the coefficient of t inside our cosine, so 2 pi divided by omega naught. Our frequency is just that omega naught. Our amplitude is just r, right? That's the sort of min and max displacement is our capital R. And then our phase angle is just our phi. So here phase angle is essentially where are we starting at? Because we're not necessarily starting right at the beginning of cosine, we have a shift. So that's what our phase angle is. So if we can manipulate into this special form, we can immediately spot the period, amplitude, frequency, and phase angle of our displacement solution. And it's consistent. We just go up and down and up and down and up and down and up and down and stay exactly the same forever. Since there is no damping, no external force, it's not shrinking in amplitude or growing in amplitude, and the period and frequency are consistent as well. So let's go ahead and take a look at an example. In the previous video, We found that if an object stretches a spring 9.8 centimeters in equilibrium, and the object is initially displaced 5 centimeters below equilibrium and given a downward velocity of 0.5 meters per second, then the displacement was given by y of t equals negative 0.05 cosine of 10t minus 0.05 sine of 10t. And so our job is to find the period, amplitude, phase angle, and frequency. So the first thing we need to do is convert to our alternative form. So we will convert to y equals r cosine of omega naught t minus phi. So in this case, our omega naught is just 10. R should be the square root of C1 squared plus C2 squared, so negative 0.05 squared plus negative 0.05 squared. So this just should be 0.05 times the square root of 2. And then we have negative 0.05 should be equal to 0.05 times the square root of 2 times cosine of phi. And negative 0.05 should be equal to 0.05 times the square root of 2 times sine of phi. So we get negative root 2 over 2, or negative 1 over root 2 is our cosine of phi, and that's also sine of phi. Let me update quickly. So this first equation was from C1 equals, the second equation was from C2 equals. So that first equation, if we divide through by 0.05 root 2, that's negative root 2 over 2 is equal to our cosine of phi. Same thing for the other. If we divide through by 0.05 root 2, we get negative root 2 over 2 is our sine of phi. And we wind up therefore getting that phi, let's see, that principal angle should be pi over 4 to have those as our cosine and sine with ignoring the sines. And then we have cosine positive and sine positive. Cosine negative and sine positive. Cosine negative and sine negative is third quadrant, and then cosine positive and sine negative is fourth quadrant. So we're in the third quadrant with principal angle pi over 4. And so we wind up with negative 3 pi over 4 as our phi. So our phi should be negative 3 pi over 4. So we are looking at y is equal to 0.05 times the square root of 2 times cosine of 10t, and then plus 3 pi over 4. Our period was 2 pi over omega naught. So we are looking at 2 pi over 10 or pi over 5. And our units are seconds. Our amplitude is just our capital R, which is 0.05 times the square root of 2. Our amplitude should take our Y units, so this is meters. Then our phase angle this is phi, was negative 3 pi over 4. The units for that is radians. And then our frequency was omega naught, which is just 10. So we have 10 full cycles per second. So again, this is what is referred to as harmonic motion because it just stays consistent. It's just a simple trig function going on forever. And this is the characteristics of that harmonic motion. So if we have an undamped free system, we get this very special case.